All right, good day, everyone. Before we get started, do you have any questions? Okay, so I guess we can get started. All right, so we're gonna take a look at section 1.4, 1.5 today, as well as 1.6. Okay, so I want you to open the PowerPoint from the Blackboard course. And then we're going to talk about some linear functions, also the application, mathematical models built based on the linear functions. So let me just quickly talk about the function notation, right? Before we go to all this actual content. Okay. So first of all, the standard notation, so far we're learning something like y equal to mx plus b. This is what we call a standard notation. So if you have y equal to mx plus b, we know this is slope-intercept form of the linear equation. And we can also use a function notation. So function notation here is x and y, right? So for function notation, we're looking at it as a specific function. So f of x equal to mx plus b. So this is the difference between those two notation. So good thing about function notation is anytime when you have a specific x values given here. So for example, here the x is what we call the independent variable. And then y here is called a dependent variable. So y depends on x. Okay. So x is definitely independent. X could take any values, right? So for example, let's say we have something like, we have an actual function. Let's say f of x equal 2x plus 1, right? So using the function notation, anytime you pick x value, let's say x equal to 1, then you're going to get a corresponding y values here. So in terms of function notation, you could do f of 1, right? Because x becomes 1 now. Okay, so f of 1 equal to 2 times 1 plus 1. So that's why it becomes f of 1 equal to 3. And same thing here, right? If you're using standard notation, you get y value equal to 3. So let's say y equal to 2x plus 1. When x equal to 1, then y equal to 3. And from the standard notation, we get order pairs, right? 1, 3. And for the function notation, it's more flexible, meaning anytime we put in the x value, let's say we put another one, x equal to 2, then f of 2 should be 2 times 2 plus 1. So it's 4 plus 1, that becomes 5. Okay. So given x value, we get a corresponding y value, but it's in the function notation. And sometimes function notation brings some convenience, in terms of expressing the relationship between two variables. Okay, so just give you an idea of what we're looking at in terms of standard notation and function notation. Okay, and let's go back to the PowerPoint. Okay. All right, so we're gonna look at linear functions. Okay, as specifically what I mentioned earlier, it's f of x equal to mx plus b, right? This is in the slope-intercept form. Okay, slope and then y-intercept. M is the slope. B is what we call the y-intercept. Okay. And then we're going to take a look at how we generate mathematical models, using the linear function. Okay. So mathematical model using, actually last class we talked about the depreciation, right? We're actually using a linear function to model the depreciation process for machine, for the computers, for any for properties, you can depreciate the value of that subject. So mathematical modeling, this is very important, application in using mathematics, and you can use that to solve a lot of real world problems. So first of all, you come up with there are 4 steps in this process. You come up with a real world problem, you formulate the problem, then after that you come up with a mathematical model, right, to model this particular problem. Then you solve using the mathematical model, and after that you try to interpret it, interpret using the real world concept. So that's basically the process of mathematical modeling. Formulate, so given a real world problem, we first need to formulate the problem using the language of mathematics, right? For example, we can formulate, if you can turn into a linear function f of x equal to mx plus b, that'd be good. And then you can utilize that, to maybe make a prediction about given x values, and then come up with the corresponding y values. So, and then after that, we solve it using the model we built, right? So, so we solve it using so once mathematical models has been constructed, we use appropriate mathematical technique, some algebra, right? Most of the time we're using some algebra to handle the manipulation, and also come up with a correct solution, okay, to solve the problem. And after that, we need to interpret using the term related to the real world. So you obtain some result, but you still get to apply to the actual problem, right? To make sense of it, okay, and using the actual context, okay. Now after that, you can test the model. So some mathematical model of real world application describe the situation with complete accuracy. For example, let's say you want to deposit some money into a bank account. So you want to give the exact accumulated amount in the account at any time. And in that case, you come up with a model and then use a model to best describe the account balance in your bank account, right? So that's how this thing works. So now, again, let's go to the functions. Typically, function, we're using function notation. So f of x is what we are using, right? You also see like g of x, could be any letters, h of x, right? They're actually equivalent to y, right? So they are the same as y. So any function notation you are utilizing, they are equivalent to the y value, to the standard notation we are learning so far. So let's say a manufacturer, example of this could be a manufacturer would like to know how his company's profit is related to production level, right? So you try to model this using mathematical concepts. And another example could be a biologist would like to know how the population of a certain culture of bacteria will develop over time, right? When the time changes, how this bacteria changes. Okay, so this could be some idea, how you can model things using the mathematical models. So in each the example we described, we're concerned about the same question. So how does one quantity depend on another quantity? So this another quantity is what we call the independent variable x, right? Because it depends on that. So this is independent variable. X, right? And then another quantity, this quantity is dependent variable. So it depends on the independent variable. Typically in the standard notation, we use y to represent the dependent variable. So relationship between the two quantities conveniently described in the function notation, like f of x equal to, for example, if it's linear relationship, it's mx plus b, right? Or it could be a quadratic, right? Let's say f of x equal to ax squared plus bx adding c, right? So this is a quadratic function. Okay. So a function is a rule, right? We assign to each value of the x, y, and only one value of y. So basically, the function notation tells us that one x value could only produce one and only one. One and then only one y value. So that's why it's called one-to-one relationship. One and only one y value, right? So all the function relation is one-to-one relation. Okay, so like the example went over, right? Anytime you plug in the x value, you only get one y value out of it. And that's why it's a function. So that's why it's one-to-one. If you plug in the x value, you come up with two y values. That's not a function notation. I can give you an example, right? For example, let's say you put in this y squared equal to x, right? So anytime you plug in the one x value, let's say x equal to 1, that means y squared equal to 1. And when you're taking the radical here, radical y squared equal to plus minus radical 1. So that means y value equal to plus minus 1. So now in this particular relationship, it's not a one-to-one relation. It's not a function. It's one-to-two relation, meaning one x value produces two y values. So it's not a function. So that's why it's not a function. So we look at it from pure algebraic perspective to analyze it, come up with the conclusion about this function relationship. Any questions so far about the function? Okay. So let's say, and let me take a look at that example. So number y is normally equivalent to, as I mentioned, y is the same thing as f of x, right? Just under different notation, right? Y is a standard notation, f of x is a function notation. And the example of function may be drawn from a familiar relationship between the area of the circle and the radius. We know that area of the circle, we're using a, right? That equal pi r squared. Now here, what if you assign area as a variable y, assign radius as a variable x. So now it becomes y equal to pi x squared. And this is what we call a standard notation. It doesn't matter what kind of letter we are using, right? It's still expressing the same relationship, meaning the area of the circle depends on the radius of the circle. Okay, so it's pi times radius square. Okay, so here, for example, let's say a radius equal to 5 maybe inches, right? Then the area should be pi times 5 square, which is 25 pi. So a equal 25 pi. So it's one-to-one, right? Anytime we plug in one measurement of the radius, we get a measurement for the area. Same thing here. Here, y equal pi x squared express same relationship. Here, when x radius equal to 5 unit, and the area of the circle equal to pi times 5 squared, right? So x becomes 5, so 5 squared, that becomes 25 pi. So it turned out to be same result. Okay. So just give you an idea, how this thing plays out. Although we are using different variables, but they express the same relationship. And here is one-to-one relation. It's a function because anytime when you plug in one specific radius, the measurement of radius, we only get one area associated with that. Okay, so now using the function notation, changing the y to f of x, right? So we get a pi times x squared. So now this is a function notation. Okay. So now similarly, if you want to compute area of the circle with a radius of 5 inches, just like what we did earlier, right? So here, f of 5 represents the area of the circle when the radius of the circle is 5 units, 5 inches, right? So this x becomes 5. So now it becomes 25 squared is 25 pi. Okay. And f of 5 here representing the area of the circle when the radius equal to 5 inches. Okay. And now here, just do the calculation, and we know that x refer to the independent variable, right? It doesn't change, right? X could take any values. And the variable y here, or f of x, is what we call the dependent variable. So dependent variable depend on the independent variable. And all the possible x values called the domain of the function of f of x, right? So x represent all the possible x value is the domain of the function. And the y, all possible y value is the range of the function. So x associated with domain, y associated with the range. Okay. And typically they are expressed in the interval, right? So just some background information on the function. And here we go back to the linear equation, y equal mx plus b, right? M is slope, b is y-intercept. So now in order to express in the function notation, again, y becomes f of x. So you get an mx plus b. And that's how we define y as a function of x, by using this function notation. And then the domain of the linear equation is all real numbers. All real numbers, right? Meaning all the numbers possible out there. And range is also all real numbers. And then our real number, we also, if you want to put into the interval notation, it will be negative infinity to infinity, all real numbers. So interval notation will be from negative infinity to infinity. Same thing here. And then this symbol indicates infinity. It's a Greek letter infinity, right? Okay, meaning infinity is not a concrete number, right? Infinity is a number which keep increasing, right? That's a meaning of behind infinity. Okay, so now we look at this, the graph of the linear equation straight line, and straight line is expressed in this f of x equal mx plus b. So we call this linear function. Okay, so the linear function is defined using this expression, right? Here m is a slope, is a constant. B is the y-intercept. They're both constant. Okay, that's important. Okay. So linear function plays an important role in the quantitative analysis of business and economic problems. Okay, so now let's look at some of the simple depreciation, right? The one we mentioned last time. So the following example illustrates how how to derive equation describing the book value of the asset. Okay, or you can book value of the asset and being depreciated linearly. Okay, and we call this straight line depreciation, right? It's an important term in the accounting and finance field. Straight line depreciation. It's actually an application of the linear equation, depreciation. Okay, and we're using this linear function, right? To linear function is utilized to model this situation in this field. So a network server has an original value of $10,000. Okay, and it's to be depreciated linearly over 5 years. Okay, so this is the life of the asset, right? With 3,000 scrap value, meaning scrap value is what we call the remaining value, right? Or residual value, scrap value, residual value. Meaning after 5 years, the network server is worth $3,000, right? Although originally it's worth $10,000. So now you want to find the expression given the book value at the end of the year T. Okay, and what will be the book value of the server at the end of the second year, right? Meaning when T equal to 2. And what is the rate of depreciation of the server? Okay. So those are the questions we try to figure out. So here, original value tells us that when time T equal to 0, right? When they first purchased the network server, meaning that's when the time T equal to 0, and the value of the machine, V of T, equal to $10,000. Okay, so this is first condition given. Second condition is when T equal to 5 years, after 5 years, right? The residual value, VT, equal to $3,000. So the value of the machine, value of the network server depends on the time T. Okay, so here time T is what we call the independent variable. Independent variable. And a V of T is a dependent variable because the value of the machine depends on the time T. Okay, so that means we're gonna apply a linear function utilizing those two variables. So first of all, we can use this, put it into the order pair, right? So dependent X value goes first, 0, 10,000. Okay, and the other order pair is 5 and 3,000. And we know that in order to set up the linear function, we need to know the slope. So slope, we're using this formula, x1, y1, x2, y2. Right, so plug it in. So you get 3,000, that's y2 minus y1. Y1 is 10,000. Divide by 5 minus 0. This is negative 7,000 over 5. And this turned out to be negative 1,400. The meaning of this is the value of the server will go down $1,400 per year. Okay. And this is the interpretation of the slope. And we know that y-intercept here is actually b here when x equal to 0, y-intercept is 10,000, meaning the initial value of the machine, of the server is $10,000. And now once you have slope and y-intercept, then we can set up the linear function for this, right? So value of the machine, V of t equal to m times x plus m times t. Here the variable is t. So instead of using x, we're going to change it to t. M times t plus v. Okay. So v of t should be equal to negative 1,400 times t, adding 10,000. So this is the linear function we use to model this scenario or this real world problem. And next step is when you have the linear function, then they want to figure out what happened when time t equal to 2. Then you can just replace time t with the 2, right? And then get the remaining values of the server. So here, okay, so this just show you all this analysis. So slope first, right? So you get negative 1400. And once you have that, we're just using point slope formula if you want to do that, but we identify, y-intercept b, equal to, this is b, right? When x equal to 0, then we have y-intercept b, right? And we get that, then we come up with the model, right? Linear function to model this. And after that, we plug in the 2, right? Because time t equal to 2, here replace x with the 2. Replace t with the 2. And we get a remaining value should be $7,200 up to 2 years. And that's the remaining book value of the server after 2 years. And the slope, we know that it's negative 1,400. So that means annual depreciation is $1,400, meaning as 1 year go by, the value of the machine will go down $1,400. Okay. Any question on this depreciation question? Okay, very good. So now once you graph it, right, you can just put in the y-intercept here, 0, $10,000, that's initial value. And as the time goes by, actually it's decreasing, right? Meaning as time goes by, the value of the machine goes down. And when t equal to 5, we get 3,000. Then you get 2 order pairs on the graph, 2 points, connect them, extend it. And the thing about this is, you see, the value machine, this line actually has limitation, right? It doesn't, since the residual value is 3,000, meaning so the value doesn't go below that. So only on this part, right? So linear model only applied to when time t equal to 0 all the way to 5, right? It doesn't go beyond that. Go beyond that, there's no meaning behind it. So here the domain, right? Domain meaning all the possible x values should be from 0 to 5. And the range, meaning all possible y values, is from 3,000 to 10,000. Just give you how this thing works out, right? So this particular linear equation has limitations based on the domain, right? Because you do not depreciate after 5 years. Okay. A lot of real world problems has very specific limit, right? Meaning it doesn't go extended on all possible x values, right? It only it has a limitation, it has restrictions, you have to stay within a certain range and then a certain interval. Okay. So that's what this is. And now let's take a look at another important topic called the cost, revenue, and the profit functions. Okay. So now are we assuming they all linear relationship, right? For the cost function, revenue function, profit function. So for any business or any like manufacturing companies, any business we're talking about, there are 3 important elements: cost, revenue, and profit. Right? Cost is like what they call the bottom line, and then revenue. Revenue is what drive the business moving forward. You have more revenue compared to the cost, then your business will last longer, right? It just keep going. So that's 3 important elements in any business or manufacturing companies. So first one, let's take a look at a cost function, right? So X denotes the number of units of product manufactured or sold. then the total cost function is C of X equal to total cost of manufacturing X unit of a product. So C of X should be, if assuming each unit costs C dollars, right? And you have X unit, so C times X. Okay. All right, so that's how you define the cost function. And revenue function is the total revenue realized, from the sales of X unit of the product. So if each unit is sold for $20, for example, then the total revenue should be 20 times X. And the profit function is the revenue, the total profit realized from manufacturing selling X unit of the product. And the profit function comes from revenue function, total revenue minus total cost. Right? So that's a relationship among those three things. So generally speaking, the total cost, revenue, profit functions associated with the company would probably be nonlinear, right? So this is very possible, right? It could be a nonlinear relationship. Then we have to model the situation using different mathematical models. But linear cost, revenue, and the profit function does happen in the real life. For this course, for this particular topic, we consider a linear relationship existing in cost, revenue, and profit functions. So now, going forward, right, we're only talking about linear relationship. Okay. So for the cost function, that's always two parts, right? We have a fixed cost and a variable cost. So the cost function comes from two types of cost, variable cost and a fixed cost. Let me give you an example what those fixed costs is, right? Could be, let's say you are a manufacturing company, and the fixed cost could be the rent of the, let's say the rent of the office, right? So that will be a fixed cost, right? Or like the salary of your full-time employee, that's also fixed cost, right? Salary of all the employees, that's a fixed cost. The variable costs come from anytime you making one product, right? And you need to use some material, or you also need to use electricity, and also all like raw materials utilized to manufacture that, then that's a variable cost. Right? So meaning as more units produced, more costs incurred. And in terms of fixed cost, it doesn't change, right? The rent of the office always stays the same, right? The salary of the employee usually stays the same. So it doesn't go up or down based on the unit produced. But the variable cost depends on the unit produced. It could be the raw material used, could be the electricity used to produce X amount of the products. Does that make sense? Okay. So this is the cost. And costs vary with production. Sales is called variable cost, as I mentioned to you. So let's say 10 unit produced, 20 unit produced, we have different amount of variable cost. Example of the variable cost, cost for raw material, right? So for raw material, 10 units produced, amount of the raw material used is totally different from 20 units produced with the amount of raw materials, right? So if you produce 20 units, you use more materials. So suppose, firm has a fixed cost F dollars, right? Meaning all the salaries, rent, all those like, taxes, all that fixed cost. A production costs C dollars per unit, and selling price of X dollars per unit. Meaning when you produce a unit, it costs C dollars. Okay. And then when you sell the unit, you collect S dollars. Okay. So now the cost function could be generated using C times X. C represents cost per unit times total unit produced plus the fixed cost, right? So this is cost function. Revenue function equal to X unit. It's the unit sold as S dollars per unit, S times total units sold. Okay. So that's revenue function. And the profit function is revenue function minus cost function. So it will be X times X, S times X minus parentheses C times X plus F. When you expand, you get this. Even better, if you want to factor out the X, it should be S minus C times X minus F. And also here, this is what we call a slope, right? If you look at the from the linear equation, this is what we call slope. And then negative F is what we call the y-intercept, right? Same thing here, C is what we call the slope. F here in the cost function is what we call the y-intercept. Here S is the slope. The y-intercept is 0, right? We can just add a 0 to that, so there's no y-intercept here. Y-intercept is 0. Okay. So all of this is a linear function, and linear function has two important elements, slope and y-intercept, right? So once you separate them, you will be able to get that. So they are linear functions. Now let's take a look at the actual problem, right? So profit function for Puretron water filters. So this manufacturing company, they manufacture the water filters. Okay, it has a monthly fixed cost of $20,000, production cost of $20 per unit, and then selling price of $30 per unit. So you want to find the cost function. So the cost function comes from two parts, right? A fixed cost, $20,000. Okay, we're adding that. And also variable cost is $20 per unit. And they're producing X unit. So it's 20X plus 20,000. Okay. That should be the cost function. And revenue function, each unit sold $30, right? So let's say you sell 10 units, you get 30 times 10, $300. Now, if you sell X unit, it will be 30 times X unit, you get 30X. Now the profit function, P of X, is revenue function minus cost function. So it will be 30X minus 20X, adding 20,000. And once you expand it, you get 30X minus 20X minus 20,000. And this turned out to be 10X minus 20,000. Okay. So this is a profit function. Okay. So for the cost function, slope M is 20, y-intercept is 0, right? For the revenue function, slope is 30, and the y-intercept B is 0. Okay. And for the profit function, slope M is 10, and the y-intercept B is negative 20,000. That's for the profit function. If you want to graph all three of them, you can do that, right? And let's see. So we figured out all three different functions here. Yeah, that just, again, this the detailed work. Any question on this specific example? All right.
So, Professor.
Yes.
So just with this function, X is just like literally just a character. It's not going to be solved or anything.
Yeah, it's not. Yeah, but maybe let me ask you something. So break even is very important for any business, right? Meaning at least you can stay alive. For any business to stay alive, they have to break even. What do you think of the break even point for this water filter company?
You're asking me how I would discover the break even point?
Yes. What do you think?
I would think to break even, like you have to achieve equilibrium. So I would think that's an instance where you would have to find the X independent variable where I guess.
Yeah, very good.
Yeah.
So we try to locate how many units do they need to produce in order to break even. So that means when break even happens, meaning profit function equal to 0, meaning there's no profit, right? Revenue equal to cost. That's what this means. Break even is revenue equal to the cost. Total revenue equal total cost. That's when break even happens. When this happens, meaning profit function equal to 0. So that tells us we can just set 10x minus 20,000 equal to 0 because that's profit function. Now we can solve for x by adding 20,000 from both sides of the equation. Then we get 10x equal 20,000. And we divide 10 from both sides of the equation, we get a total quantity need to produce and sold, x equal to 2,000. Meaning, as soon as this company produce 2,000 units and sell 2,000 units, then they break even, meaning they stay alive. They could move forward. At least, as soon as they break even, they could keep producing more units.
Okay, cool.
Yeah. So if they produce more units than 2,000 units, they will make a profit, right?
Mhm.
So if they produce less than 2,000 units, they will have a loss. So that's how business analyze their financial conditions and make sure they stay alive. They can make more money, in the future, just by mass production.
Okay, cool. Thank you.
Very good. So now let's take a look at more sophisticated case, right? So now we're gonna do a complete analysis on this manufacturing process, including the revenue, cost, revenue, and profit function. So let's go through this. And this question actually is from your textbook. So consider a manufacturing process that produces 7,500 units at a cost of $650,000, 10,000 units at a cost of $850,000. And each unit produced could be sold for $100. And we are assuming a linear relationship exists between the number of units produced and the cost, and then find the total cost function, revenue function, profit function, and given the units of M and B. And also second step, find the variable cost per unit, also known as the marginal cost and then the fixed cost, right? So the fixed cost, we know that the marginal cost is same equivalent to the variable cost per unit. And also we want to find out what is cost, revenue, profit when 60,000 units are produced. Okay, and then let's find out what is break-even point, and also the average cost per unit of producing 25,000 units, and the equation of the average cost per unit function. And this question also appear in your second project, right? So you also want to pay attention to this. And so on Friday, you'll be able to, figure out the answer for that last question in your project number 2. Okay. So now, first of all, I'm gonna put this into the note, and I'm gonna show you how to do this step by step. Okay. First of all, let me just. Okay, here. Let me just erase this and then put in the note. And you can also think about how we can solve this question, right? Print screen. Okay, print a note. And let me share the screen with you. So the first thing we do is we're gonna come up with all 3 functions, right, as a part 1. Okay, so first one is a cost function. So let's look at the cost function first. And based on the question, they tell us 2 different scenarios. One of them is unit produced. You see, unit produced here is X, right? We call this X. And also the cost is what we call the Y, right? Y values. So based on this, we have 2 order pairs. When 7,500 units produced, the cost is $650,000. And if there are 10,000 units produced, the cost turned out to be $850,000. You want to put dollar sign in front of it. It's okay. $50,000. Okay. So just like any, in the equation, when you are given two order pairs, so here, let me just unit produced, sold is produced. And we are assuming here, all the unit produced will be sold, right? You have very good salesperson, so all the unit produced, they will sell it. Okay, so we assuming this is X, right? So in this case, Y value here is the cost of producing X units. Okay, so this is Y. And that's why we have all the pair XY, XY, right? So now this is X1, Y1. This is X2, Y2. Now, first thing we can do is find the slope. Using slope formula, Y2 minus Y1 over X2 minus X1. And then again, we throw out the numbers into the formula. So it's 850,000 minus 650,000 and dividing by 10,000 minus 7,500. Okay, so simplify a little bit, we get 200,000 on top over, and 10,000 minus 7,500 is 2,500. Okay, now you divide into that, get $80. Okay, $80 per unit, right? So if you want to look at this, this is per unit. Meaning the cost of producing one unit is $80. Okay, and if you produce 2 units, it will be $160, right? If you're producing 10,000 units, it will be $80,000 and $800,000. Okay, so that's what this means. Okay, so now since we have this, the function notation, so now next thing is getting the equation of the line using point slope formula. So you do y minus y1 equals slope times x minus x1. And we know the slope, $80 per unit. We know x1, we know y1. Now we throw into the this formula to get the equation for the cost function. So y minus 650,000. Let me do a better job. Minus 650,000 equals slope, which is 80 times x minus 650,000. No, that's no. So y1 is 650,000. So x1 is 7,500. So we have that 7,500. Now you're going to expand it, right? And then simplify. So 80 times x, 80 times 7,500. So y minus 650,000 equal 80x, and 80 times 7,500 will be 600,000, right? Minus 600,000. Okay. And next step, we're just gonna add in 650,000 from both sides of the equation. And we simplify that, y equal 80x plus 50,000. Okay, so now we go back to the cost function, right? The function notation using c of x to represent function of cost. So c of x equal to 80x plus 50,000. And in this cost function, we know slope m is 80. And the y-intercept b, it's going to be 50,000. And does anyone want to point out what do we mean by this? The meaning behind this. What does 50,000 represent? The actual meaning. The y-intercept b.
The fixed cost?
Very good. Yeah, this is a fixed cost, right? Very good. And how about $80 here per unit? It's what we call,
Variable costs.
yes, very good. Variable cost per unit. Very good. Per unit. So by understanding the meaning behind this, each one of this actually helps a lot. So you know how this linear function was applied here, and also provide some better understanding of this particular situation. So this is the first step. We find out the cost function. Actually, revenue function is slightly more straightforward because they tell us that each unit is sold by for $100, right? So the revenue function should be each unit $100, right? We have X unit, so 100 times X. And then here for this revenue function, slope is 100. Okay, and then y does B is 0, meaning there's no revenue when 0 unit produced, right? That makes sense. I mean, if you sell no products, you do not get any revenue, right? So when X equals 0, B equals 0, meaning no revenue when 0 unit sold. Okay, but the slope here indicates this is what we call the verb. This is slope is meaning $100 per unit, meaning you get $100, $100 revenue per unit. Okay. And B equals 0 here indicates no revenue when 0 units sold. There's no sales, no revenue. Okay. And we interpret both slope and y-intercept here for revenue. And also the third thing is a profit function. So we know that profit function, so this is a cost function. Let me label this cost function. And we have a revenue function. And we have a profit function. And the profit function equal to revenue function minus cost function. So total revenue minus total cost is, they call that gross margin, right? Or like gross profit. So this is 100x minus 80x. Make sure you put 80x plus 50,000 in the parentheses. Otherwise, there will be confusion, once you do the calculation here. Because C of x, the whole thing should be in the parentheses. So it's 100x minus 80x minus 50,000. And let's look at it, right? So this turned out to be 20x minus 50,000. Now, let's look at the slope here. Slope is 20. Anybody know what this means? And then y-intercept B is negative 50,000. Anybody want to interpret this too? What does slope indicate here?
Is it indicating a loss?
Okay, yes. Meaning y-intercept B, right? Negative 50,000 indicates when 0 units sold, the profit is negative 50,000, right? Okay, that means, yes, you're right, it's a loss, right? So when 0 units sold, profit is negative 50,000, right? They have a loss of $50,000. You're right.
Yeah, because the cost.
Exactly, because of fixed costs, right? Right here, fixed cost, 50,000. It's always going to be there, right? Like the salary of the employee and the rent, it's always going to be here no matter what, no matter how many units you sell, right? It's going to be there. Yeah, especially when 0 units sold, you definitely have 50,000 losses, Yeah, so that's, how about the slope? What does slope mean? It's like $20 profit per unit, right? Meaning every time they sell a unit, they generate $20 profit. So $20 profit for each unit sold. So they sell one unit, they get $20 profit. They sell another unit, get another $20. If they sell 10,000 units, they get $200,000 profit. Okay. So they just give you some, general idea about all this slope and wind design, and it's important because when we move forward, we need those. So now the second step is they want us to figure out what is the variable cost per unit. Okay, what do you think? What is variable cost per unit? Let's go back to the cost function, right? The cost function is this, and m equal 80, that's a variable cost per unit, meaning every time the company produce one unit, it costs $80. It varies, right, based on the units produced. Okay, so this is $80 per unit. And we also know variable cost, right? We did the analysis earlier. Variable cost per unit. We also know the fixed cost is $50,000. Okay, and that's the second part. And the third part, how do we find out the cost revenue profit when 60,000 units are produced and sold? What do we do? We have all three functions, right? Now, what if 60 units, meaning x equal to 60,000 units? You just have to plug this into all three functions. Plug into the cost function, you get a total cost. If you plug into the revenue function, you get a total revenue. And if you plug the x into the profit function, you get a profit. So we're gonna do that, right? So first of all, C of 60,000. We want to find out the cost of producing 60,000 units. So here x becomes 60,000. So it's 80 times 60,000 plus 50,000. And this is 4,800,000 adding 50,000. Okay, and this total cost becomes 4,850,000. Okay. And this is the total cost for producing 60,000 units. And then revenue of when 60,000 units produced, total revenue should be, again, replace x here with 60,000. So we get 100 times 60,000. And this turned out to be 6 million. They have revenue 6 million, cost of 4 million, almost like 5 million. So they have a million something profit, right? And we can find out the actual profit by plugging 60,000 into the profit function, P of 60,000. So now I'll go back here, replace x here with 60,000. So it's 20 times 60,000 minus 50,000. This is 1.2 million, 1,200,000 minus 50,000. And the total profit turned out to be 1,150,000. Okay, so this is total profit of producing 60,000 units. So the company is doing good if they're producing 60,000 units and they sell all of them. Okay. So this is part 3, and part 4 is break-even point. Okay, so that's we did it earlier, right? With the other example, in order to break even, we have to make sure revenue equal to cost, meaning we want to make sure profit function. So profit function equal to 0, meaning no profit, right? No loss, no profit. So here indicating 20x minus 50,000 equal to 0. So we have a linear equation, and with the one variable x, you just have to solve for x. So adding 50,000 from both sides of the equation, and we cancel that. 20x equal to 50,000. Okay, and then just divide 20 from both sides of the equation, we get the total quantity needed to break even. So this turned out to be 2,500 units. Okay. So meaning, as soon as the company producing 2,500 units, they could stay in the business, right? They do not generate a loss. And if they produce more than 2,500 units, they make a profit. But if they produce less than 2,500 units, then they have a loss, which is not good, right? For loss for a business is not very good. Okay, so that's part 4. Part 5, you want to find out average cost per unit of producing 25,000 units and the equation of the average cost per unit function. Okay, so any suggestion? How do we find out average cost per unit for producing 25,000 units? Okay, so in order to find out average cost per unit, we need to know the total cost, right? So 5, we're going to find out the total cost first. Total cost of producing 25,000 units. Total cost of producing 25,000 units. Okay. So we look at the cost function first, right? So the cost function C of x is 80x plus 50,000. Now here x equal to 25,000 units. So replace x with the 25,000. So we get C of 25,000 equal to 80 times 25,000 plus 50,000. So this turned out to be 2 million. Okay, this 80 times 25,000 is 2 million. Adding 50,000. Okay, then total cost turned out to be 2 million and then 50,000. Okay, so we know the total cost using that. So average cost per unit is using the total cost over total unit produced. Total cost over unit, total units. We know total cost is 2 million and then 50,000, and dividing by 25,000 units, right? And let's see what that is. You have to put it into the calculator. I think it's going to be $82. $82 per unit, but let me double check. By 25,000. Yeah, it is $82. And think about this. So meaning average cost per unit is $82 per unit. And we know $80 is variable cost, right? Where does that $2 come from? Any suggestion? Why there's extra $2 here? Anybody figure out that? Because we know that variable cost is $80 per unit, right? And remember, we have fixed cost. And when we spreading 50,000 fixed cost over 25,000 units, then we know that each unit costs $2. That's where that $2 come from. So it's a variable, it's a fixed cost spreading over 25,000 units produced. That's why it's $2. And that's why average cost here is $82 per unit. Very important, right? Very interesting analysis here. $80 variable cost is always the same, and the fixed cost changes. So think about when you're producing 25,000 units, fixed cost is $2 per unit. What if you're producing 50,000 units? Then the fixed cost is $1 per unit. And that's why for all the manufacturing companies, for any companies, they always want mass production, because the more units produced, they could spread out the fixed cost. Eventually, when you make enough units, the fixed cost becomes irrelevant, right? What if you're making 2 million units, then $50,000 fixed cost over 2 million units, that will make it a very minimal impact on the cost. That's why they always want to, and they will always give you discount, to buy more. You see, that's why they won't do that. All those companies. Okay. All right. So very interesting phenomenon in the business. So we figured out average cost per unit when 25,000 units produced. But what if we want to find an equation of the average cost per unit function? So remember, we do this average cost. So I'm using this AVPC, right? AVPU, average cost per unit function. And let's use A of X, right, to represent it. So we know that is total cost over total units. Total cost come from the cost function, right? Cost function C of X over total units X, right? So this turned out to be 80X plus 50,000 dividing by X. Okay. And then if you spread out, if you divide into that, you will be able to tell, here. So 80X by X is 80, right? And we call this variable cost per unit. And then the other element is 50,000 fixed cost by X. So in this case, when X increases, then the average cost per unit function decreases. So you can increase X values, right? So X increases, then A of X decreases. Okay, so it's like the opposite direction. They move in the opposite direction. So the more units produced, sold, the less cost, the smaller the average cost per unit. Yeah. So that's why, you see all that, you can make sense of all those, like all those big companies, Coca-Cola, that's why they try to, sell the beverage in a very big pack. So the more they sell, the less cost, the less cost they will generate, right? In terms of average cost per unit. So they can make more profit. So it's very, very good, question. Also give you a lot of insight into these manufacturing companies and in terms of revenue, cost, and then profit. Okay, do you guys have any question on this? Okay, we should definitely go over this one more time, and then we have some homework questions in the back. Maybe let's go to the section 1.4, 1.5C. Let's look at some of the questions from the textbook. So let me go back to our textbook. Okay. Yeah, let me open the let's open the textbook, right? You guys also open the textbook really quickly. Let me see any interesting question in the back of the textbook. So we should go over and so also help you, do your homework. All right, let's go to section 1.4 and 1.5. And I don't think there's not much difficult questions in the back of 1.4, 1.5. We did this already, and 1.4. Let's look at it. Okay. And this one, just asking us to create 5 order pairs and using any 2 order pairs, calculate the ratio of the change in y with respect to ratio of the change in x, right? So basically you just calculating the slope, right? That's what you have to do. And maybe let me take a look at some of this, the ones, it doesn't give us very explicit, equation, right? Like question number 8. Let me do that one. Okay. All right. Let's go to this. Okay, so I will focus on question 8 since it's a little bit more complicated. Okay. So 8, first of all, the equation is not expressed in the slow intercept form. That means we need to do some transformation here. And so we need to turn into a slow intercept form by using some algebra, right? Algebraic manipulation. So distribute it first, you get 6x minus 12, adding 3y equal 3x. So now the only thing we want to keep on the left is the 3y. Okay. We don't want 6x, we don't want 12. That means we got to subtract 6x, we're adding 12 on both sides of the equation. Remember, when you perform operation on the one side of the equation, you have to do the exact same thing on the other side.
I can't see your writing.
Okay, I probably didn't share the screen yet. Okay, sorry about that. Okay, here we go.
Thank you.
All right, so yeah, I just basically copied the question 8, and first step I distribute it, right? And we get a 3 times 2x, 6x, 3 times -4 is then minus 12, and adding 3y equal to 3x. So now what I did is I need to keep 3y on the left. So subtracting 6x, adding 12 from both sides of the equation. So once we do that, 6x get canceled, 12 get canceled on the left. 3y, that's what we want on the left. And 3x minus 6x is negative 3x, and carry over 12. And we do not combine the variable term with the constant, right? Because they are different things. Variable terms stays as is. Constant stay as is, right? We can only combine a variable term with a variable term. Like 3x minus 6x, we combine that, we carry over the 12. Right? There's no number to be combined here. So now next step, we're gonna divide 3 from both sides of the equation. Right, so divide into that, y equal to negative x, negative 1x, if you want to put invisible 1, adding 4. Okay, so now we have the equation. Yeah, so after that, we want to generate 5 order pairs from this equation. It shouldn't be a difficult task, right? So you can come up with your prefer like x, y values. Okay. So maybe I start with I use the natural numbers. So 0, 1, 2, 3, 4, right? And this is not the only way to do it, right? You can pick other things, right? You can do 2, 4, 6, 8, 10, right? No problem. 1, 3, 4, 5, 7, 9. All the odd numbers, all the even numbers. Theoretically, you can pick any number you want. Okay. So the y value, when x equal to 0 is negative 1 times 0, adding 4, that turned out to be 4. Okay. And then the second one, y value, negative 1 times 1, adding 4, is minus 1, adding 4, that turned out to be 3. Okay. As you can see, when x increased by 1 unit, y value go down by 1 unit, right? Because of slope is negative 1. So they move in the opposite direction. X increases, y value decreases. So the next number must be 2, right? Next number must be 1. Decrease by 1, becomes 0. Okay. And what they want you to do is pick any 2 order pairs. Okay. Just pick any 2 you want, right? Let's say you want to pick the second order pair, 1, 3. And you want to pick a fourth order pair, 3, 1. And you want to calculate the slope, right? So using the slope formula, so you do, so y2 minus y1 over x2 minus x1. This is 1 minus 3 and then over 3 minus 1. So this turned out to be negative 2 over 2. And that's become negative 1. If you go back, it should match with your slope here. Okay. And that's how we verify the slope using any two given order pairs. And take a look at this. Do you guys want me to go over any other even questions in the section 1.4? Are you good with this? Okay. They look pretty similar.
Could you do number 9?
Number 9, it's your responsibility. Okay, so I can't do the odd ones, right? Odd ones is your homework. That's why I only do the even ones. Okay, so I'm gonna give you a tip, right, on this. You just move this 2y to the left. I mean, you know what? It's okay. I'll do it. But you still gotta, let me get you started on the question 9. Okay. So for question 9, we get a 2x adding 3y, 2y minus 7x. So now, first of all, we want to combine all the variable term with respect to y. So we do subtract 2y from both sides of the equation. And the reason I move 2y because 2 is smaller than 3. So we will avoid the negative coefficient by doing that. So cancel the 2y, we get 2x plus y, 3y minus 2y is 1y, right? So equals minus 7x. Now from there, you subtract 2x from both sides of the equation. We get y by itself. So we get a y by itself on the left, minus 7x minus 2x is minus 9x. Okay. So now once you have the equation, now set up the table, throw in the numbers, get all the pairs, then you get the slope, right? Okay, so I leave the rest to you. And yeah, I take care of the algebra part. Okay. All right, any other question you want me to go over, or are you good? Okay, so this is exercise 1.4, and let's go to exercise 1.5. See anything, interesting there? Okay, yes, this one has a lot of interesting questions, so let's look at it. So question 2, it's about the cost of rent a car, right? Usually they have a fixed cost. In this case, the fixed cost is $185 per week. They also have a variable cost, right? 40 cents per mile. So meaning for additional mile we drive, it costs 40 cents. So, all right, so then let's set up a linear equation here to model this specific scenario. This is also a real world scenario. If you go on a vacation, you need to rent a car, this is what happens, right? Usually for most car rental company. So the total cost, we can assuming weekly rental cost. So you should also assign these variables, right? We use C of X, right? Represent this. And then also mileage driven in a week. We're using X, right? Let's say X miles driven in a specific week. So you need to define both of them, right? So now the total cost come from 2 parts, right? We know that it costs 40 cents per mile. So it's 0.40 times X mile, right? That will be the variable cost. And then the fixed cost here is $185. So adding the fixed cost, $185. And that turned out to be the total cost. And this is the cost function for renting this car. Okay. Any question on this? Very similar concept, right? So, and this one has you see the depreciation. Okay, it depreciates 10% of its original purchase price, right? Meaning slope is 10% of the total, the initial value. Okay, so yeah, the slope is negative, right? Okay. How about question 4? The amount of water used by a hotel when there are no gas, it's 2,000 gallons per day. That means this is fixed amount of the water use, right? And then for each guest, they use about 150 gallons per day. So the equation you create will relate total water use per day to the number of the guests in the hotel for that day. Okay. Anybody want to come up with the equation here for question 4?
Would it be 150x plus 2000?
Yes, perfect, right? So give me what will be the variable we are using? What is x here?
Oh, is the number of guests?
Yes, very good. Number of guests. Perfect. What variable are you using for the total water used?
Y would be the total use.
Okay, that's fine. Y will be total amount of water used. Very good. So the total amount of water used come from 2 parts. First one is fixed part. The other one is variable part. So fixed part, we know that is 2,000 gallons, right, per day. And then variable part, each guest, we use 150 gallon. We have X amount of guests. So Y equal to 150X plus 2,000, right? If you want to use a function notation, you could do f of x equal to 150x plus 2,000. But no problem, right? You can use either one. Either one is good. But yeah, definitely great answer. Okay. All right, let's see. Any other interesting, maybe question 6. Okay. Question 6, archaeologists working on a dig site, that every inch of the depth represents 500 years of age. The equation you create will relate the age of the layers to its depth. So any suggestion for this?
Would it be 500x?
Okay, 500. Okay, so what does x represent?
Inches?
Okay, inches of the depth, right? Very good. Okay, or maybe just depth in inches, right? So maybe that's even better. So maybe let's put in this way, the depth of the dig site, the depth in inches. Okay, and then what does y represent?
Total years of age?
Yes, total years of age. Very good. Years of age. So what y equal to, so 1 inch represents 500 years, right? So that means 500 times x. Very good. Okay, that should be the answer. And if you want to use a function notation, it will be f of x equal to 500x. Okay, very good. Okay, let's look at the question number 8. I'll probably do a couple more, and then we're gonna move on. Okay, so then question 8. Let's look at this. It is estimated that 40,000 acres of farmland are lost to development in New Jersey each year. There are approximately 800,000 acres of active farmland in the state in 2006. Create an equation related amount of farmland left to the number of years that have elapsed since 2006. Okay. Okay, any suggestion? First one, let's define x, right? what will be the x here? What will be the variable part? What changes? Time changes, right? So x represent number of years. And what is y here?
The acres.
Yeah, exactly. It will be the remaining active farmlands, right? In acres, remaining, like a remaining active farmland. In acres, you're right, totally. Okay. So now, let's think about the first scenario. Is if there were approximately 100 acres of active farmland in the state in 2006, we can assuming time t equal to 0, right? So in 2006, that's assuming t equals 0. Okay. And we're going to have this, right? We're going to have order pairs first. So time t equals 0, we have 800,000 acres. Okay. So we have a point, right? We have order pair here. And what else is given here? What is this 40,000 acres per year? What does that mean? You see, it's estimated that 40,000 acres of farmland are lost to development in New Jersey each year, meaning as a year go by, the number of farmland go down by 40,000 acres, right? So this is exactly the slope, isn't it? Slope representing as the x value increases by 1 unit, meaning as a year go by, then the number of farmland, acres of farmland go down by 40,000. So this is opposite. It's like the negative slope here, right? So it's negative 40,000 representing the decrease, right? Meaning farmland decreases over 1 year of time. So negative 40,000 per year. Okay. So now we know x1, y1, right? And we know a slope. And we can use point slope formula. Y minus y1 equals slope times x minus x1. To find the equation of the line. Okay, so y minus y1 here is 800,000. That's initial, that's the amount of farmland back in 2006. We treat that as initial time. So slope is negative 40,000. X here is 0, right? Okay. Now you just distribute it and combine like terms. So y minus 800,000 equal negative 40,000 times x, right? Negative 40,000 times 0 becomes 0. Okay. And the last thing, you have to isolate y by adding 800,000 from both sides of the equation. Then we cancel that to y by itself. So we get negative 40,000 x adding 800,000. Okay. So let me ask you something. When at which year there will be no farmland left? Can we figure out that? At which year? There's no farmland left. Any idea?
When y equals to 0.
Yes, very good. Y equal to 0, right? Okay, so that means negative 40,000 x equal to plus 800,000 equal to 0, right? And then next thing, you could just solve for solve for x by subtracting 800,000 from both sides of the equation. Keep the variable on the left. So you get negative 40,000 x equal to negative 800,000. Now, next thing, you divide in negative 40,000 from both sides of the equation. And then that x turned out to be 20, right? what this tells us is after 20 years, so initial time t equals 0 is 2006, right? Now t equal to 20, meaning 20 years later at 2026, there'll be no farmland left in New Jersey based on the development, based on the current rate, right? So in 2026, no more farmland. So this is kind of important issue for the for those government agencies, right? They have to think about this. You see, within next 5 years, 5-6 years, there will be no more farmland. So if they want to develop, let's say if the population go up a lot in New Jersey, right? They have to think about some other ways to to farm. So yes, something to think about. Okay. So this is question number 8. Okay, now calculate the slope using 2 points and equation. Okay, so this is very similar to the one we did earlier, right? So just get 2 order pairs from the equation, and then also using slope formula to calculate the slope. Okay, that's what you're supposed to do. I think that's it for that. And then let's quickly take a look at section 1.6, right? And just take a look at some of the graphing tools we utilize to graph the linear equation. Again, it's still kind of review from the algebra course, right? So let's open that. All right, and let's look at section 1.6. We probably couldn't finish today. It's okay. We're gonna finish next Wednesday, right? We'll get started on section 1.7 next Wednesday. Okay. Let's open the PowerPoint in a second. Meanwhile, any questions so far? What we learned today in the class. Feel free to bring up the question. And open it. So in section 1.6, we actually looking at how we graph the linear equation. We have several different methods, and let's look at it, right? So we have 3 different kind of form, general form to represent the linear equation. And we try to understand and use the slope-intercept form. We use that a lot. We also use a point slope standard form of the equation. We also use a point slope formula, right? So 3 important forms. And it's summarized in the next page. Okay, so first slope-intercept form, and we can, if you know the slope, you know the y-intercept, we could graph it, right? By plotting the y-intercept first, and then using the slope to generate another point on a graph and connect them. You can also use x-y-intercept, right? Find the x-intercept, find the y-intercept, and then graph it. We also could use point slope form to graph, right? So we're going to get into those details in a second. And which form is used to graph x and y-intercept? Any idea? It's when you have a general form, right? Ax plus by equals c, right? This is what we call general form. When you have something like that, it's most convenient to use x-y-intercept, because we can easily find x-y-intercept from this particular form. Okay, so this is what we call the standard form. Okay, so now, yep. Let's look at it. Very form of equation of the line, slope-intercept form. Okay, given slope and intercept, right? Y-intercept. And we have a standard form. Okay, ax plus by equals c, right? A, b, and c are integers. And then a is greater than 0, a must be positive. Okay. And then point slope formula, we already learned this. Given a slope, given a point, And point slope formula is most convenient way to get an equation of the line. Now let's take a look at the actual problems, right? So cheat sheet. Okay, equation in the standard form, then use intercepts. Okay, XY intercepts, right? Slope intercept form, then you get a slope and intercept. Then we generate another point connected. And is in neither form, and choose the method you like the best. Okay. So we will get into this. So first of all, let's take a look at this question, telephone costs, right? In the community, the monthly cost of a local telephone service is $5 per month plus 25 cents per call. So first of all, let's get the equation, right? To represent this scenario telephone cost. So that's X representing total number of calls, right? And then Y should representing total cost, right? Total monthly cost. So the Y should be equal to, we have two costs, variable cost, 25 cents per call. So 25 cents, you translate it to dollar amount is 0.25, right? 0.25 cents. We have X amount of calls, X, adding fixed cost, $5. Okay, so now in this, so we know the y-intercept here, slope M is 0.25. Okay, and then you turn into a fraction, it's a quarter, right? 0.25 is a quarter. So now the y-intercept B equal to 5. So first of all, from there, we come up with the y-intercept, right? The 5, okay. So y-intercept, when x equals 0, y equal to 5. Okay, so here. Okay, so we get the first order pair, the y-intercept, first point on the line. Now we're going to use the slope. Slope is quarter, meaning you go up 1 unit, go to the right 4 units. So from here, go up 1 unit, go to the right 4 units, 1, 2, 3, 4. So now you get that. So based on these two, you connect them, extend it, you get a line. Okay. All right, that's how you get a line. The second point is right here, right? By using the slope, go up 1 unit, go to the right 4 units. Okay. So you get that. So that's how we get the line, using the slope, both slope and y-intercept. Okay, and then we also have slope intercept form. 0b, right? So the y-intercept is 0b, slope. It's still, just, okay, so now graph y equal 2x minus 4. So the slope is 2, y-intercept is -4. So if you want to graph this really quickly, okay, so y-intercept is located on the y-axis. Okay, so -4, -1, -2, -3, -4. So the first order pair, first point is right here. Let me use a different color. First point is located down here. Okay. Another point based on slope. Slope is 2 over 1, meaning it's up 2 units. And then go to the right 1 unit. So go up 2 units, and you stop at -2, right? And then go to the right 1 unit. Now we get another point. Now extend it, collect them, extend it, right? Then we get a line. So this is y equal to 2x minus 4. Okay. So using slope and y-intercept is fairly quick process to get that. Okay. And if you want to graph, it should be x. All right. Which graphing method is easiest? It's a slope intercept form. It's easiest. Okay, so now let's take a look at this. So the slope here is, it's -1/3, and then the y-intercept is 2. So we start with the y-intercept 2. I'll put that into the, okay, y-intercept 2, 1, 2, right here. Start with that. Now using the slope, b equal to 2, use that, get a y-intercept. Now slope is -1/3. And this -1 meaning go down 1 unit. And 3 represents go to the right 3 units, right? Right, 3 units. So go down 1 unit, stop here, and then go to the right 3 units. 1, 2, 3. Okay. So now we stop at here. So we basically have 2 order pairs. Okay, so connect them, extend it, you get a line. So this is the easiest way to get the line here. And what if you are given the equation in this form? Okay, you are given equation in -2x plus 3y equal 12. Now it's easier to use xy intercept. So first one is find the x-intercept. Because we don't see the slope, we don't see the y-intercept. So it's easier to just find xy intercept. So when finding the x-intercept is setting y equal to 0, that means -2x plus 3 times 0 equal to 12. So -2x equal to 12. So divide -2 from both sides of the equation. So x equal to -6. So the x-intercept is -6 and 0. And second step, find the y-intercept. In order to find the y-intercept, you set in x equal to 0. That means this x becomes 0. So we get -2 times 0 plus 3y equal to 12. So this is 0 plus 3y equal to 12. And dividing 3 from both sides of the equation, y equal to 4. So the y-intercept will be 0, 4. And now once you have both order pairs, we can graph it, right? So y. The x-intercept is -6 and 0. It's located on the x-axis negative side, right? So let's say this is -6. And then y-intercept is 4. Okay, so 4, this is 6, that's 4. And you can just connect those two and we can get the line. Okay. Both x, y intercept. Okay, now we get a line. Okay, 5 primary 3. Okay. And that's how we utilize. So the important thing is get an x-intercept and y-intercept and graph it from there. Any question on this? Okay, I guess I will stop here today. So if you have any, I can stay for another 5 minutes. If you have any question, you can talk to me about it. Okay, otherwise I'll talk to you guys on Friday. All right?
Okay, thank you.
No problem, guys. Bye-bye.
Thank you.
Thank you.
Bye.
See you on Friday. Bye.